All right, this is Crucial Python Week 8. We're going to be covering Joblib and how to write a parallelized for loop really easily with it. And there's our logo. So Joblib is actually a module that does a lot of different useful stuff like caching the output of functions, logging, but today we're pretty much just going to be focusing on its capabilities for parallelizing code. So the two important members of Joblib that will help towards this end are parallel and delayed. And you are basically going to end up using both of them when you write something that looks like a parallelized for loop. Delayed is actually just a decorator, and it returns a list of tuples of the function and its arguments, and that is what then gets passed to parallel. Parallel constructs a class, and you call that class with a list of tuples, where each tuple is the function and its arguments, which is, again, what delayed outputs. And parallel then runs through each of the entries of the list and calls the function over and over again. So it's not terribly important that you follow that. The more important thing is just to get used to the syntax. So here's a simple example where, using list comprehension, we're computing the square of the numbers from 0 to 10. And here is how you do exactly the same thing using Joblib parallel. So it looks somewhat similar. There's some additional syntax here, but the result is exactly the same. And the reason that parallel is important is because you can actually pass it this nJobs parameter. And instead of just running through the for loop sequentially, it'll actually do iterations of the for loop at the same time using multiple cores on your CPU. So here I'm telling parallel to run 8 jobs at the same time, and it will have exactly the same result. And so this is, squaring the numbers from 0 to 10 is not a terribly interesting thing to do, and it's also not particularly computationally expensive, which is usually where parallelization is useful. So for a more practical example, here's a function called convolveRandom, which takes in a size. It generates 2 random arrays of that size, and then it convolves them. And if you're not familiar with what convolution does, it essentially just takes 2 arrays and it computes their pointwise product and sums it, and then shifts 1 array by 1 sample, does it again over and over and over again. So for big arrays, this can be computationally expensive because you're computing so many products and sums. So if we define our function and then run it with a length 40,000 array and time it, it takes about a second to run, which is, starting to get to be something that you might want to parallelize. If we just run it sequentially over and over again, and so these are calls to it which use sizes from 40,000 to 47,000, yeah. And if we use list comprehension like this, it just does it sequentially. So one job is running, the next job is running, the next job is running. There's no parallelization, but we can do the same thing using parallel and delayed, and what this will do is, instead of running them sequentially just like above, it'll run them potentially all at the same time, depending on how many cores you actually have. So it's taking a second to run because it takes a while, but so this is just now telling me that it took 8.69 seconds to run it sequentially without parallelization, and about 2.88 seconds with parallelization. So that's it's almost a factor of 3 speed up, which is pretty good. It's not a factor of 8, and maybe we'll get to why that's true a little later. But first, another reason that parallel is nice is that it has some other useful stuff that got wrapped in. It's actually just a wrapper around multiprocessing, which is a built-in Python module, but it has some additional functionality that, in addition to just being useful and simple to use, which multiprocessing isn't really, it has some additional stuff. One of them is this verbose keyword, which basically allows you to tell it to print out messages as it runs through the jobs. You can also interrupt it with Control-C, which is useful and can mess up multiprocessing. So if we run convolveRandom again from 16 times, but we set this verbose parameter to 50, then that basically just tells it, okay, every time you do a job, print out and tell me you did the job. So here it's saying, okay, I finished one job at 2.1 seconds. second job at 2.2 seconds, and so on until it finishes at 6.6 seconds. So that's all great. One of the things that you're going to have to think about, though, is when you should actually use parallelization, because it's not always the right thing to do, and it's also not always clear how many jobs you should run. My laptop that I'm running all of this on has 4 cores, 8 hyperthreads, but 4 actual cores. And so what I wanted to do was basically come up with a way to, really simple way to measure how much faster parallelization actually is for different functions that take different amounts of time to run, and also how many cores is the smartest to use. So this is some code that will do that. I encourage you to run it on your own machine. It's up on GitHub, and just because it'll help you get an idea of, when you should use parallelization, what kind of speed up you can expect, and how many jobs you should run, and so on. So essentially what I'm doing is I'm going to be running that example convolution function that I described earlier, and I'll be running it with array sizes from 50,000, 10,000, 15,000, and so on up to 50,000. And I'll also be trying different settings of the parameter and jobs from 1, 2, 3, 4, all the way up to 8, which is what max jobs is here. And then this is the code that actually runs it, and I'm not going to run it right now because it takes a couple minutes to try all these parameter settings, but I did run it earlier, and I'm just going to load in the results from earlier. So you see when you run this cell, it saves out a text file with numpy, and here I'm just loading the times back in. So the first thing we can look at is basically at what point does it become useful to actually do parallelization, because for really fast functions, it's actually not beneficial to parallelize because there's overhead in setting up all of the threads. So if it's a really fast function, it might actually be to your benefit to not parallelize. So if we look at the running time on the y-axis against the number of jobs for the first 4 sizes, so this is when they were length 5,000 arrays, 10,000, 15,000, and 20,000. You can see that when the size was 5,000, it actually was faster to only have 1 job. When you add a second job, it makes it go a little slower, and then you can actually see that as you increase more jobs, there's maybe some kind of trend upwards there. So basically the parallelization overhead is hurting you. But as soon as you get to 10,000, that's not really true anymore, and then when you get up to 15 and 20,000, you kind of see the expected trend, which is that it's faster to use 2 jobs than it is for 1 job, and then faster to use 3 than 2. But that trend doesn't necessarily continue, and if we plot this instead, maybe we can get a better feel for why that is. So here I'm plotting the size, the correlation size, or the convolution size against the running time. This first line is for 1 job, this second line is for 2 jobs, and so on. You can follow the legend to see how many jobs corresponds to each line. And kind of like we saw in the graph above, it was faster to go from 1 to 2, and then maybe from 2 to 3, but then beyond there it kind of gets a little bit washed out. And that is probably due to the fact that my computer only really has 4 cores, and so it might not be beneficial to use all of my CPU to try to have more jobs than I have cores. But actually an interesting feature of this graph is that for the 8-core case, it actually seems to be faster than the other number of jobs, and that could be because of the hyperthreading stuff that Intel does. But at any rate, this is just a really simple, fun experiment you can do to see how much parallelization will actually help you. So I encourage you to run it. And that's it.